talking about the rheology of complex fluid in general, and more specifically about the suspension of elastic particles. Those elastic particles, in this case, are called capsules. Those capsules present some kind of similarities with emulsions or with drops, whether on a single particle level or on a suspension level. So I first will start with a brief introduction to complex fluid for those who are not that much familiar with the topic. So complex fluid describe a wide range of substances found almost everywhere in our daily life. So typical examples include household products, so such as shampoo, mayonnaise, beer, or simply biological fluids, for example, such as blood or mucus. So they are termed complex, not just because of their composition, but also because of their rheological properties. So it's a multiscale problem involving many body interactions, and of course that would lead to a complex rheology, where the viscosity would be a function of several variables. So capsules, in this case, consist of an elastic thin membrane enclosed in a fluid with properties that can be similar or different from the suspending fluid. They have a typical size spanning from roughly 10 nanometers to 10 microns. They are characterized by some kind of shape memory, in the sense that it is possible to recover the original shape of the capsule after stopping the source of external stresses, provided that the membrane is still intact, so you don't have membrane rupture. Capsules are mainly used to transport and deliver active substances by either membrane breaking or diffusion. And both phenomena happens at two different time scales. So the diffusion is quite slow and happen in the scale of a couple of seconds, and the membrane breaking, the transport to membrane breaking basically happen in the span of microseconds, basically. So in order basically, so we are doing numerical simulations. So in order to reproduce the membrane mechanics, we model the membrane using the elasticity of the membrane using a 2D elastic law, which is valid for thin membranes. Our capsule, or the surface of the capsule, is meshed with triangular mesh. And usually the capsule has two modes of deformation. So shear deformation, so resistance to shear deformation, and resistance to area dilatation. And basically, depending on the constitutive, in addition to conservation of volume, so depending on the constitutive law that one would use, one can have both features or only the shear deformation. So in this case, one can basically classify the mechanics of the membrane of the capsule into two classes. The first class is what we call the strain-softening capsule, where basically, if we apply an external stress, the capsule will deform, and the deformation or the elongation will increase with the increase of the external stress till the rupture of the membrane. So this is kind of similar to basically drops. And the second type of capsules is the strain-hardening capsules. And in this case, basically, when you apply an external stress, the resistance of the capsule to the stress increases as well. So the membrane presents some kind of nonlinear behavior with the as function of basically the applied stress. And these are basically the type of capsules that we are interested in this kind of work. So I'll be studying, as I said, rheology of capsules. So I have a dense suspension of capsules. I am applying a shear flow. I have a bit periodic domain along the X and Y direction. I'm applying a velocity boundary condition, a Zuhi boundary condition. I am solving the fluid flow using Lattice Boltzmann with the Bigelow collision operator, and the membrane deformation or the computation of the strains are done using a finite element, and the coupling between both the elastic capsule and the fluid is done through the immersive boundary method. A typical size of my capsules is usually 8 times delta X, and the particle Reynolds numbers is in all of my simulations smaller than 0.03. So I am in the Stokes regime. I fix the confinement, and my variable will basically be the number of particles or the volume fraction, and the capillary number, which is a dimensionless number, which basically quantify the resistance of capsules to external forces. Later on, we will see that this definition is actually, or this capillary number is not exactly correct because it cannot capture all the properties of a capsule, of a strain hardening capsule. Then I have also another dimensionless parameter, which is the local inextensibility. So these parameters basically say that if C is quite small, you allow local dilatations or local increases of area. And if C is large, so basically you prevent this. So my motivation basically is to understand the rheology of capsules. So basically to compute the viscosity and to try somehow to find the relevant parameters that describe the rheology of strain hardening capsules, and maybe simplify by reducing the number of parameters. So generally speaking, so for suspension of colorways, the viscosity depends on large number of parameters. So the size of the particle, the density of the particle, the number density, the parameters of the fluid, so basically viscosity and density of the fluid, the temperature, the external stress or the shear rate, and time sometimes. Then basically, if you take some assumptions, or if you introduce dimensionless numbers, and then you take an assumption that basically you neglect thermal fluctuation, you end up by having a viscosity that depends only of 3 variables. And then if you go one step further and consider that you are in the Stokes regime and you don't have any kind of Brownian motion, so basically you end up by having the viscosity, which is only function of one variable, which is the number of particles, the volume fraction. And the viscosity basically can be just described with a second order polynomial if you stay in the semi-dilute regime. In my case, since the particles are deformable, so again, I have a bit more variables. So I have viscosity, which depend not only from the number of particles, so volume fraction, it also depends of the capillary number and of this C parameters, which is related to the local inextensibility of the capsule. So we start with basically doing a benchmark where we take a single capsule, we apply a shear flow, and then we measure some of the important quantities. So the first quantity would be the elongation of the capsule. And then we also measure basically the orientation of the capsule with respect to the flow direction. Then we measure also the intrinsic viscosity of the capsule and the first normal stress difference. Then we compare the results that we have with basically existing literature. So we did compare our results with front tracking method and boundary element method. And we found basically a quite good agreement. The only problem now is that if you want to compare, if you want to move one step further and go toward the semi-dilute or concentrated limit, there is nothing in the literature to compare with. So basically, we found ourselves being the first people doing this. In 2018, Marco Rossi and Luca Brandt basically proposed a model where they studied these strain softening capsules, which are basically behaving roughly like drops. And they basically measured the viscosity as function of the volume fraction. And they observed that these strain softening capsules also show a shear thinning behavior, so similarly to drops or to emulsions. And in addition to this, basically, they propose an effective volume fraction by including the mean deformation of the capsules, and found out that you can obtain a universal behavior or a collapse of the viscosity on a single curve that is basically an Euler curve. And they also basically use the same the same logic for other type of data. So in this case, red blood cells, and they also found out that their model basically, or this effective rescaling everything with effective viscosity, lead basically to a collapse of the data on an Euler fit. So starting from this, we thought, okay, maybe we can use the same method and see if we can also basically get a universal behavior for our strain hardening capsules. So we start as well by measuring the relative viscosity as function of the volume fraction. And we also observe basically that we have a decrease of viscosity. If you take a look to the inset, we have a decrease of the viscosity as function of the capillary number or the shear rate, if you wish. So this is basically what we call a shear-thinning behavior. So this is also similar now to emulsions or similar to strain softening capsules. Fine. Now, when we try to do the same basically scaling as proposed by Luca Brandt for data with different C parameters, so we end up basically by having a collapse of the data, let's say till an effective volume fraction of roughly 0.15, and then we basically have deviation. And we then start thinking, what could be the reason behind this? So we went back basically to the single particle case and tried to compare basically what would happen from a geometrical point of view, and compare this basically to the strain softening capsules from the simulation of Luca Brandt to understand if we have to add something else to the model. So we measured basically the deformation or elongation of the capsules, which is shown in figure A. And we have basically, and then we also decide to measure also the different radii of the capsule. One has to keep in mind that the deformation of the capsule, which is using the formula of Luca Brandt, is basically taking into account only the first and the third radii of the capsule. So the second one is not taken into account. And when we check the different radii of the capsule, we observe basically that there are some kind of non-monotonic behaviors occurring that cannot be that are not exhibited in the deformation. So there are basically information that are missing when you use the elongation alone. And what exactly is happening is that basically, if you have, let's say, a strain softening capsule, like in case of Luca Brandt, or if you have a red blood cell, the steady state shape is more or less a discoid shape. Now, if you consider a strain hardening capsule, for the same flow parameter, if you increase this local inextensibility of the capsule, then you have basically some kind of transition from a discoidal shape to a quasi-spherical shape. And later on, we realized that the deviation are basically due to this change of shape. So instead of using the effective velocity as defined in the paper of Luca Brandt, one can basically introduce, one can basically introduce a function with a variable which is function of basically the local inextensibility of the capsule, the capillary number, but also the orientation of the capsule. And at the end, basically, we could observe a collapse of the data by doing this, and that the data basically follow an Euler curve. So this is more or less a generalization of what was basically described in the case of in the paper of Luca Brandt, and this is basically a generalization that takes into account the orientation, but also the 3D shape of the particle. So whether you have some kind of discoid, or if you have a spherical, quasi-spherical, or an ellipsoidal particle. So
sorry, 5 minutes.
Yeah. 5 minutes left. 5 minutes. Okay, I'm almost done. So now we try to do the same thing for the mean deformation of the particles. The question again is, could we observe any kind of universal curve for the deformation? So in this figure, I'm showing basically the deformation for two values of this C parameter. So basically for ellipsoidal particles, if you wish, and then spherical particles, or quasi-spherical particles. So the approach that we use basically is trying to find some kind of effective capillary number that instead of only taking into account the shear elasticity, but it will also take into account the area dilatation in the formula, and also the change of the intrinsic viscosity. So by redefining the effective capillary number, we can also end up by having a quite nice universal behavior for the deformation that can basically be described by a simple fitting curve. So conclusion, so this was basically the first study of dense suspension of strain-hardening spherical capsules. I dare to say that basically, since I came from continuum mechanics and I used to work with integral equation before, this work could not have been done basically with, let's say, boundary integral method, or something equivalent, because it's hard to parallelize this kind of codes. And the obvious choice for us was basically Lattice Boltzmann in this case. We observed a shifting behavior for these strain-hardening capsules. We managed to observe or to obtain a universal function of the viscosity, which take into account changes of shapes, so from discoidal basically to quasi-spherical shapes. Similarly, we also obtained a universal curve for the mean deformation. And last but not least, so in principle, we can use basically capsules as a model to replace, let's say, drops in soft glassy materials, because basically capsules, the mechanic of capsules allow you to tune for the same set of parameters the elasticity and have a transition from a system which would behave more like emulsion, like in the first movie, or more or less like a suspension, like in the second movie here. So yeah, thanks for your attention.
Good, thank you. Any question from the audience? Okay, just a curiosity from my side. How many particles are you able to simulate in one box with the actual code? I mean, are you thinking to small systems or to big systems?
So in this study, basically, the largest number of particles that I simulate was around 500 particles, okay, corresponding roughly to a volume fraction of 0.5. In other studies, basically, I simulate from 1,000 to 10,000 of particles.
Okay, so you can tune the volume fraction quite independent. I mean, as you wish. Okay.
Yes.
Okay.
Yes. I mean, I also went basically to a volume fraction of 0.8 okay, in another study. So,
okay. Thank you. Any other question?
Welcome.
If not, thanks again, Aouane, and we can move to the next speaker, which is Matteo Lulli, with a presentation titled Shan-Chen Pressure Tensor Anisotropies, Another Dimension for Reducing Spurious Currents. Please, Matteo, yes, you can share your screen and you can start your presentation.
So, do you see the screen?
Yeah.
Okay.
After 50 minutes, I will give you a sign that 5 minutes are left. Okay?
Okay, very good.
Please.
So, good morning or good afternoon, everyone, according to where you are. I am Matteo Lulli, and first of all, let me thank the organizers of the conference. Really, it's great that we can still exchange our ideas. I think it's very important in this moment, and really, I'm thankful for the organizers for pulling this off. So my talk is about the anisotropies in the Shan-Chen pressure tensor. And this work has been done in collaboration with Xiao, Luca Biferale, Sbragaglia, and Giacomo Falcucci. And the talk is pretty technical, So I revealed to you already who's the murderer. And basically, as you can see in the picture on the left, below you have an 8th order forcing isotropy, which has this current intensity, this map, and we can still shrink them by enlarging the isotropy order of the pressure tensor. Now I will tell you how. So let's talk about the setup. We're using 2D simulations. So these are the details for the Lattice Boltzmann, which most of you know. We use a D2Q9 set of discrete velocities with the speed of sound 1/3, the square of the speed of sound 1/3. We use the collision operator with a Guo forcing scheme, and so that the equilibrium velocity is written this way. And in all equations, all repeated indices are going to be summed upon. The multi-phase Shan-Chen model, which has been first introduced in 1993, 1994, basically couples neighboring points in the grid along these vectors, forcing vectors EA, together with a set of weights that depend only on the square norm of the vector. And rather than having the speed of sound, we have a second order isotropy coefficient as a constraint. I'll tell you more about this later. And basically, the pseudopotential is a function of the density. And for an appropriate choice of psi, and for G less than a given critical value, which less than 0, the system shows phase separation. However, it is well known in these discrete schemes that there are spurious currents in the moment your interface is curved. There are the velocity field is 0 for flat interface, but for droplets or bubbles, near the interface we can see the so-called spurious currents, which are clearly an unwanted feature of the scheme. Why do these currents appear? Basically because of the low order forcing isotropy, which for the single belt that is reported on the left is only 4th order. How to tell this? One basically does a Taylor expansion of the forcing. And as you can see, there is this tensorial structure in the sum that is pretty relevant. First of all, no odd order can survive because of the symmetry of the forcing vectors. And the isotropy, as we will see later, is typically achieved by imposing that these tensors are only proportional to the fully isotropic tensor of rank 2n in this case. So how did people get over the single belt Shan-Chen forcing scheme? By enlarging the set of forcing vectors. And in this case, we are using 5 different groups with this square length. And these vectors can be used either to obtain a 6th order isotropic forcing or an 8th order isotropic forcing. With this improvement has led to the reduction of spurious currents, to the possibility of rescaling the lattice while keeping the same profile for a droplet, for example. And by summing the forces, so 2 different forces coming from 2 different isotropy order schemes, it's possible to control separately the equation of state and the surface tension. So what does this mean in practice? In practice, this means that if we go and check this E tensor, we basically can do what we want, which is write it only as a function of the fully isotropic tensor for the 2nd, 4th, and 6th order. For E6, we cannot do this anymore for the 8th order, and there you have these 2 corrections, I8 and I8 1, which, however, turn out to be 0 for the 8th order scheme, so that we can still write it for the 8th order, but you cannot write it anymore for the 10th order, and so on. So an important point of view that one can use is that the weights can be thought as of degrees of freedom, in a sense. So what you typically do to get the values of the weights is that you impose the 2nd order normalization, which is however arbitrary in a sense, it's a common choice. It's a useful choice, but it's still a choice. And then you have the isotropy condition that here are listed up to the 8th order. And these isotropy conditions are basically the coefficients that multiply the non-isotropic terms that we wish to avoid. Another important step is that rather than thinking about this condition for the overall weights, for the whole set of weights, we can still think about the tensor E as something that emerges for each group separately, so that we will have in front of each tensorial structure a coefficient that only depends on the chosen group. Another important feature of the Shan-Chen model is the fact that you can define a lattice pressure tensor. This was done by Aouane in 2008, and this is the interaction pressure tensor that need to be summed to the kinetic pressure tensor that we all know from the Chapman-Higgs-Kong expansion, which is basically the density times CS square, and it's clearly isotropic. So the starting point is the local definition of the force from the pressure tensor. Then one considers the integral form. So a volume integral equals this boundary integral for the pressure tensor. And this has been transposed into a lattice expression, which is this one. And basically, one is interested in analyzing the total number of contributing forces that have a flux through a given area, which is this given area element, which is this F mu A of K. Here we are restricted our attention only on a given forcing direction, which can be written as an average force times the number of contribution times the force direction. We briefly describe how to construct this lattice pressure tensor. And basically, let's start with the sum of the contributions. Basically, each vector these are the two area element in 2D. Each vector that only touches, like E5, either with the tail, either with the tip, the area element counts 1/2 because there is going to be another area element that shares the same vector. And whereas all the vectors that cross count 1. So here we have 1/2 plus 1/2 as reported below. For E13, we have 1/2 plus 1 plus 1/2. And for E17, the situation is a little more complicated because we need to distinguish which area element we are considering. So for the X area element, we only have these two vectors, so 1/2 plus 1/2. Whereas for the Y area element, we have all of them contribute with 1/2. So the whole overall contribution is equal to 2. So what is this overall contribution equal to? It was noticed that this contribution is basically the scalar product between the force direction and the area element, and the oriented area element. So that basically we can finally write down the pressure tensor contribution of the direction A in this way, which is very simple. And the other step is to compute the average force, which it's a little more technical, but I just give you the simplest case of E5. So basically, the average force is the weighted average of the contributing force intersecting the area element. And as you can see, you have the sum of the weights, which is 1 in this case, and then the weight multiplying the force contribution. And that's it. And there you have, in the last line, the total, the pressure tensor contribution by the direction 5. So let's look at the overall result. As you can see, some of the groups are the first two groups are very simple to write. 4 and 8, square length 4 and 8, there is this further contribution. Whereas the square length 5, it's rather more complex, but still, that's the lattice pressure tensor. One important property is that of the lattice pressure tensor is that if one looks at the flat interface, the equilibrium condition of the flat interface is that the normal component of the pressure tensor to the interface has to be constant. That's the mechanical equilibrium condition. And this requirement is realized, is implemented up to machine precision by the lattice pressure tensor, which is the very important property. As you can see, I reported both graphically but also numerically. And the normal component, here I report 15 digits, which is the precision of a 64 bits floating point number. And as you can see, basically only the last digits are changing through the interface, whereas clearly the tangential part of the pressure tensor has the modulation. And of course, we know that we use this to compute the surface tension. So let's discuss about the general expansion of the lattice pressure tensor, which is missing in the literature because typically people present the flat interface expansion, which is more straightforward to derive. And we do this by separating the contribution of each group, each vector group again. So at the second order, we retrieve again the isotropic contribution, which is the bulk pressure for the Shan-Chen model that has been presented already in previous works during this conference. Whereas for the fourth order contribution given by the second derivative, we can see already that there is this Kronecker delta with 4 indices, which is the anisotropic part. And this delta is equal to 1 only when all the indices take on the same value, in this case, either X or Y. And these contributions are there. And again, if we look at the fourth order for the product of first derivatives, still we get the fourth order Kronecker delta. So this is the full expansion to the fourth order. As you can see, there is this last line that survives. Now the question is, if we implement the fourth order isotropy for the forcing, do we get rid of this last line? And the answer is no. Why? Because these are the two coefficients that I marked in red. And if we analyze them, we can see that the isotropy condition for the fourth order for the forcing is actually a linear combination of these two constraints. What does this mean? It means that if we impose the isotropy of the pressure tensor, we automatically gain the isotropy of the forcing. But if we impose the isotropy of the forcing alone, we don't get the isotropy of the pressure tensor fourth order. However, this last relation is pretty important because this one assures that the theoretical evaluation of the flat surface tension for the flat profile is absolutely independent on this anisotropic correction. And again, these anisotropic corrections pop up simply because we are doing the general expansion without reducing ourselves to the flat interface case. Why do we know this only now? The answer is because, I mean, of course, many people have already worked on isotropy of pressure tensor before, coming from Shan-Chen. We notice only now because the single belt, which has been mostly used, it already yields fourth order isotropy. In fact, as you can see, chi automatically is 0 because all these weights are 0 for the single belt, whereas lambda I automatically reduces to the forcing isotropy condition. So the fourth order isotropy is already assured for the single belt, of course, likely not for the sixth order and so on. So the issue only appears in multi-range schemes, okay, which are all second order from the point of view of the pressure tensor, independently on the order of the forcing. So how do we highlight the features of this enhanced, let's try to enhance the isotropy of the pressure tensor. How do we get the difference? What's new in this with respect to higher forcing isotropies? We do this by comparing the schemes while keeping fixed the forcing coefficients so that we know up to a given order the expansion of the forcing is the same. And then we also keep fixed this parameter epsilon that basically is the one that decides the flat profile and the surface tension. So let's go on. So here, E6P4 is the sixth order isotropy forcing and fourth order isotropy for the pressure tensor. And P2 is basically the scheme that has been proposed so far in the literature. So as you can see, we solve the system for the weights by imposing E2, E4, E6, and epsilon.
5 minutes left.
Yes, thank you. Epsilon and only one of the lambda I and chi. So there are 5 requirements with which we define the 5 weights. The first line is the previously proposed 6th order scheme. This is the new one, the red one. And as you can see from the Laplace test, there is no difference for the surface tension. We did this for 2 different pseudopotentials. And you can also see we report the relative variation of the flat profiles. The largest variation is basically 10 to the minus 11, which we can, I mean, it's a very good approximation to say that these 2 schemes yield the same flat interface macroscopic observables. And let's look what happens for curved interfaces. As you can, here we report 2 different coloring. One is in linear scale, one is in logarithmic scale. But as you can see from both of them, the new scheme on top yields significantly less extended currents in space with respect to what has been proposed so far. And we can do this also for the 8th order isotropy scheme, so we can do this step further. And please notice that in this case, we can only get 6th order isotropy for the forcing, whereas we are even in a worse position, clearly worse position with respect to the isotropy of the forcing. Still, we get absolutely compatible Laplace test profiles. And again, the new forcing scheme yields significantly less extended spurious currents. How to describe this in a more unified way? One can take the probability distribution, or just the distribution, of course it's not a random variable, the distribution of the velocities of the Mach number, of the logarithm of the Mach number. And as one can see, the new scheme in red has always the peak shifted to the left. And as we go down in the forcing near the critical point, the distribution begins to collapse. But the fact that the peak is further on the left is very important, because not only tells us that the magnitude is less, but also tells us that the extension is less. Because if one looks at 1 minus the cumulative distribution, basically we can say that looking at this peak, roughly 60% of the system has a velocity that is larger than this value, whereas for the previously proposed case, we have almost 90% of the system that has a value of the velocity larger than that one. So this is the simplest way to convey, the most compact way to convey the result. And as we can see, the results are consistent no matter the forcing, no matter the choice of the pseudopotential. So as we basically, one point that has already been stated in Sbragaglia Bellardinelli in 2013 is that the lattice force expansion algebraically differs from the pressure tensor expansion. The new point is that this implies that the isotropy condition of the forcing are not the same isotropy condition for the pressure tensor. This issue automatically only emerges for multi-range models, and we fix the relevant physical quantities in order to compare the effect of the isotropy of the pressure tensor, and we have weaker and less extended spurious currents. This is a new dimension in this sense, where to study these isotropy properties and the spurious currents, which was not there before. And we'll soon publish on the archive the preprint, and along you will find more details and codes on the GitHub repository. Thank you for your attention.
Thank you, Matteo. Any question from the audience? Just a curiosity, do you think to obtain the same results via switching the equation of state you use in order to define the pseudopotential?
No, actually, because the equation of state is basically defined for the bulk part, if you want, okay. Whereas all these spurious currents appear light up in the where there is an interface, a curved interface.
Okay. And another short question. Have you noticed some differences into the interface thickness via modifying the forcing approach, via adding higher order terms in the forcing approach?
So as for the flat interface, I mean, this kind of test we have done, which is very, very stringent, as I shown from the flat interface profiles, there's basically no difference.
Okay.
But this was on purpose. Then whether this allows this isotopic condition in a different manipulation allowed to get a smaller width for the interface might be, because since you have smaller currents, you can tame better the high gradients.
Okay, thank you. Other questions? Okay, if not, let's thank again Matteo, and just let's shrink a little bit the coffee break, so we'll start again at 11:20 as proposed by the schedule, so we have lost 6 minutes in our coffee break. Then, see you later.
Thank you very much.
The first presentation will be given by Simone Melchionna, and it is entitled The Functional Response of a Neuroreceptor by a Multiscale Lattice Boltzmann and Particle Dynamic Framework. So, Simone, are you there?
Yeah, I'm here. Hello.
Okay, Simone. You can share your screen and you can start with your presentation. After 15 minutes, I will tell you that only 5 minutes are left, okay?
Yes, sure. Do you see my screen?
Not yet. Yes, now something is happening. Okay.
I hope you see my first page. I'm not sure. Let me be sure. You see my screen move, the slides moving?
Yeah.
Okay, good. So hello, everyone. Oops, I already made a mess. So I'm very pleased to show you the result of pretty recent research in a, I would say, pretty unexplored domain. So we are talking about neuroscience, and we're talking about studying a neuroreceptor, specifically the NMDA neuroreceptor. I will tell you more about what that means. And by using a framework which puts together lattice, Boltzmann, and particle dynamics. So my affiliation is from National Research Council, but I'm also the founder of a company, Lexma Technology, which had a strong input and activity in this field. So I will tell you a little bit about Lexma. And also I'd like to acknowledge the other contributors and authors of this work. Francesco, Sauro, Fabio, Bruno, Olivier, Frank, lots of Italians and lots of French here. So what is NMDA? NMDA is it's a quite famous neuroreceptor. So it's found in the nervous system. It is very famous for neuroscience because it is key for synaptic plasticity, learning, and memory. So if something goes wrong in this receptor, which sits at the synaptic end of a neuron, then we don't behave the way we should, I think. In fact, when we take psychoactive substances, NMDA fails to work. And neuroscience is pretty interested in this receptor for drug discovery purposes, for sure, and to cure diseases like epilepsy, central nervous system disorders, and also for pain therapy. So what is NMDA? NMDA is a protein, is a receptor sitting at the cell membrane. It binds glutamate, which is its natural binding molecule, and also it's shaped a bit like a mushroom. So there is a transmembrane part and a cis and a trans side. Now I don't want to go too much into the nomenclature, but it binds also to magnesium and zinc that act as basically stoppers for the flow, for the ionic current. So basically, this receptor binds some neurotransmitters, glutamate and glycine, and this triggers passage of ions through the receptor central pore. If we remove magnesium or zinc, there is actually a second trigger that will open up the receptor. So as you can tell, there is a lot of biochemistry and biomolecules going on, and you may wonder where is lattice Boltzmann happening here. So I'd like to show you this workflow that is pretty articulated. So I'll try to touch on the most important sites here. So there is this protein that needs to be first of all reconstructed from crystallographic data, and it's very important to model the fine detail of this protein, which can be done in different ways by all atom simulations or more mesoscale or more macro scale type of means. And there is a bunch of protocols that allow us to see if we are reproducing this protein in its function, its full function. But on top of it, we need to see if currents happen through the ion pore, through the receptor pore, which tells us about the correct functioning of the object. So it is important to look at the whole neurotransmitter and neuroreceptor with global eyes, and this framework is about simulating this very complex behavior. So how can we do that? Well, first of all, we need the right techniques, and Lexma is a company that is pretty exposed in this domain. So what Lexma does is to produce. You still see my slides? You still see my slides? Well, I guess so. Anyway, what Lexma does is to develop a framework which is basically a toolkit made of several components. What you've seen before was a very standard CFD in a medical device with turbulence. What you see now is DNA translocation in a nanopore. So here there is electrochemistry going on and electrokinetics. And also you will see some red blood cells. What you see now, it's a circulating tumor cell filter, a device that is being developed by some companies around. But also Lexma focuses on physiological flows and medical flows, meaning that along the years, we've been looking to cardiovascular behavior in coronaries and carotids and other types of cardiovascular systems, but also respiratory systems. And you can see, I hope you can appreciate the diversity of elements that can be put together by respecting the laws of physics and using as much as we know in terms of fluid dynamics / lattice Boltzmann and particle or cellular dynamics. So there are more examples if you want to go on the website to see what Lexma does. This is just a first taste. In terms of the receptor, we have a pretty well-defined problem, which means reproducing a protein, a receptor, a protein in a complex environment. So the strategy that we employ here is a divide and conquer type of strategy that we've employed in the past, which means we want to reproduce in full proteins because we need to take into account chemical specificity of the solutes, but we cannot spend too much of our resources in reproducing, say, the solvent or even ionic currents for some reason, not at atomic or ionic detail. So this divide and conquer strategy is about dividing the world in something that is Lagrangian and something that is Eulerian. And in the Lagrangian side, we still need to account for the full chemical identity of its components. And so there are lots of interactions going on, intra-protein or interprotein forces, but also protein-solvent forces. again, what is about NMDA? Well, NMDA is an object that has disparate scales. If we try to solve the problems by brute force, which means atom-based, it would be impossible today. We're talking about thousands, or was it trillions of particles, and the functional response is milliseconds or minutes, which is something that is not accessible by even the largest computers. And there is a lot of action going on in terms of the intrinsic transition of the protein, which is called allostery, and I'll tell you more about it, but also about the more functional behavior of the protein, which is really where the currents happen through the protein center pore. So, and also, we're talking about something that is pretty large, but it has to sample phase space. And phase space is quite huge, and which means besides the natural time of the system, you want to sample lots of long tails of the system. So you want to sample pretty complex phase space of the whole thing. Today in biosimulations, we know that there are very large simulations being done. I cannot change my slides. Okay. Yeah, so there are lots of large simulations being undertaken by using all atoms or coarse-grained models, but no lattice Boltzmann as such. So our purpose here is to merge these two worlds in some consistent way. So clearly, this will take advantage of the largest computational facilities around and the largest platform. So again, merging particles and solvents of some kind requires to have an adaptation of the lattice Boltzmann, where we have basically the standard lattice Boltzmann core for hydrodynamics, but also fluctuations and forces that stem
Timon,
from...
I think your presentation doesn't go forward.
Doesn't move forward. Where are you now? What is the slide you see now?
4.
4.
I had the same problem yesterday. It was the browser that was the problem. So if you're using Safari, I had the problem yesterday. So maybe it's the same problem.
Actually, I'm using Chrome.
Okay.
So let's. You see any?
Yeah, I see there is an issue with the presentation.
Okay, so do you see the slides changing now?
No, try to stop the screen sharing and to start again.
Okay, what about now?
Yeah, now the slide has changed.
Has changed. Okay, I'd like to go in presentation mode.
Yeah.
Okay. So I was here. So what about now? Do you see anything?
I see solvent-solute coupling, hydrodynamics fluctuations, but you are not in presentation mode, okay? You are in the design mode in PowerPoint.
Okay.
Yeah, I mean, it doesn't matter. If you want to continue, you can continue by this way, but...
Do you see anything moving now or not?
No.
No. Okay. So presentation mode doesn't work.
Okay.
All right. So I'll do by hand type of.
Okay.
Okay. So so this solvent-solid coupling in general terms is made by a framework that allows to exchange forces that can be momentum exchange. So basically drag forces, but also solvation forces, because again, the identity of the chemical identity of species is important. The solvent has to be a solvent which has an intrinsic adhesive force, and so has to sense the presence of a hydrophilic versus hydrophobic type of atom. And fluctuations need to be in place too, because we're talking about mesoscale or microscopic type of environment. So these are basically technicalities. But going back to the chemical specificity, which is so important, we wrote a large review paper with Sauro and Massimo Bernaschi last year that displays basically all possible options in terms of modeling various solutes in complex solvents. So let's go back to NMDA. NMDA is an object that is present in the crystallographic databases, but this is usually pretty fragmented, meaning that not all information is present. So that's because some part of the proteins are in the transmembrane area, and this is not resolved by crystallography. So it is very important to reconstruct the structure, especially the terminal ends of the peptide in some way. And at the same time, we need to come up with a protocol such that we can simulate such large object. So we have put together 3 different models. One is a pretty fine-grained model for the protein, which is an all-atom type of representation. Another one is called mesograin, meaning that we reproduce the amino acids as basically simplified objects with 5 pseudo-atoms per amino acid. And then we have a coarse-grained model, which is an elastic model. So interactions are pretty simplified. So let me show a little video that tells you more about what we did in simulation. This is the NMDA embedded in a phospholipidic membrane. So it's moving small fluctuations all the time, except when these ligands bind. This is now a little bit of a cartoon, but then when they bind, the protein as such has a transition. You cannot spot it by eyeballing, but there is something that happens in the interior. So what you see in yellow is a tiny pore that opens and fluctuates a lot. So this is one channel that is about passing currents, but our opinion here is that there will be multiple channels that are not visible by this pure geometric analysis. So maybe the time is short, so I can skip all details about the protocol for equilibration of the protein in the membrane. It's very articulated. This work took us a long time and many computer resources. But the bottom line here is that you have to take a good care of reproducing the initial condition, equilibrate the system, and let go. So this is pretty sophisticated as such. And what you want to do once you have an NMDA in the membrane in a lattice Boltzmann environment, which it will be the watery solvent, is to look at the binding affinity, which means to look at the free energy difference between the attached versus detached state of the ligand. And so we have actually 4 ligands, glutamate and glycine. So this process is a rare event process, but it's so important that we need to quantify the free energy difference. So what we do here is to, we have to avoid the brute force process where you allow for the binders, the ligands, to reach the pockets in the receptor. What you have to do is to create a virtual process and compute the full thermodynamic cycle. So there is a bit of technicalities here that is well known in the molecular dynamics community, but nevertheless, the end result is that you produce this sequence of states. And what is important is the begin to end, the difference of states, and then you can quantify the free energy difference.
Simone, 5 minutes left.
Yeah. So what happens upon binding with the ligands? The protein basically transforms. It has a very fine movement with rotation of the subdomains. So these are not eye visible, and it's very difficult also to compute reaction coordinates that can quantify this type of motion because of the fluctuations. So what you do here is to look at the downstream result, which means the pore opening and closing. Okay, so this is very important. This opening and closing happens on a spatial scale of angstrom or below 1 angstrom. So it's really, really difficult to appreciate this type of opening, and you can really see something that is not reality. So first thing we did was to measure pore conductance by using an anomic type of approximation, which means we looked at the geometry and looked for the passage, purely geometric passage of ions throughout. This was not very informative and actually could have been wrong by orders of magnitudes. And in fact, it only gives you a qualitative result. So I can skip this, but this is purely geometric. But then we went into the lattice Boltzmann world, and here we did electrokinetics. So given the receptor structure, we meshed the whole thing, and we applied a voltage difference and used the electrokinetic equations that we developed some time ago. And so this is made of three components, basically: a solvent, a neutral solvent, water, counter ions, and co-ions. So it's a three actors type of dance, and we measure conductance. So conductance allows you to appreciate all possible channels in the protein in core, and what we could observe is a clear opening and closing of the receptor, and we observe this with different models, microscopic models for the membrane, and by applying different voltages. So the last part of this talk is about the gist of it, I think, which is the function dose response, meaning that given that a number of ligands that you can attach to your receptor, this is basically micromolars in terms of concentrations, and then you can look at the ion current divided by Imax, the maximum current you observe, and this matches extremely well the experimental data. So with this work, we think we have proved that we can use lattice Boltzmann and molecular dynamics for neurosciences, and to look at pretty complex neuroreceptors in function, quantitatively. And actually, I can give you more numbers about free energies and timescales and so forth. We use some approximations. For example, we have disentangled protein fluctuations from ion currents. So what we did was to extract hundreds of configurations from simulation, and to look for look at the ion currents for each of them. So this was an ensemble of ion currents, but still it's a disentanglement because we don't see the ion current as it goes through the process. So it's basically post-processing. But it's still very useful, and we believe that it is pretty close to what would be the final result. And this approximation will be further analyzed and we think will be under control. So there is work in progress into this. That's it. Thank you very much.
Thank you, Simone. We have time only for a really quick question from the audience. There.
I can ask question if there's time.
Yeah, really fast, please.
Really fast. Okay, you don't have to answer now. Then, if you think it's long. So you used the LBM, but you could also probably just continue with your MD simulation and add ions to your system and measure their exit rate.
Yeah, well, actually, let me assure you, this is impossible by all atoms or even coarse-grained models. The point is that the passage of ions through the pore is a rare event.
Yes, there are methods to enhance sampling in these specific cases, like Markov chains. But yes, I just wonder if this is much better than using this enhanced sampling.
Yeah, actually. So if you use molecular dynamics by enhancing sampling or enhancing the passage, then these are methods that are good for equilibrium conditions. But we're talking about non-equilibrium conditions with full non-linear behavior of the receptor. So for this, you need to have a method that can reach pretty high levels of Knudsen number and be able to look at the very, very tiny currents throughout the system. So Lattice Boltzmann is a great solution for this type of problem.
Okay, okay, that's interesting. Yeah, thank you.
Perfect. Thank you again, Simone. And let's move to the last speaker of this session, is Raymond Christianto, with a presentation titled Modeling Droplet Dynamics of Mesh Structures. So please, Raymond, to share your screen.
Yes, I'm okay. Let me share my screen.
Yeah. After 15 minutes, I will give you a sign that only 5 minutes are left.
Can you guys see my presentation now?
Yeah.
All right.
Please.
Does it moving? Does it do the slide change?
Yeah.
Okay, good. Hello everyone. My name is Raymond Christianto. I am from Durham University, and this morning I'm going to present my work about modeling droplet dynamics on mesh structures. So my motivation is currently there is a water shortage problem in the world. It's happening not only in developing country, but also in developed country. There are a lot of solutions which can be used, but one solution which we want to use is by using biomimicry to design a structure which can be used to do water and fog harvesting. Our starting work is from this work by my second supervisor, just Badyal. In this paper, they found a plant which is called Tuja plicata, which has this ability to collect a rain of water. After rain of water from rain, therefore water cannot penetrate the leaf and wet the soil underneath them. So Franz Perkerson et al. Studied this leaf. They studied the structure, the macro, the micro, and the nanostructure. And what they do is they imitate the macro structure, do a 3D printing of it, and then they found that it has the same water collecting ability, which is very unique because it doesn't really have any special superhydrophobic or superhydrophilic surface, no micro or nanostructure, just a simple 3D printed surface. So this make our group to be very interested. So we want to study how the structure works. We want to see how it can collect water, or when it can collect water and when it cannot collect water. And then after we understood how it works, we want to know how to improve it. And we already know that there are already a lot of works done on a flat dry surface, on a spatial surface with microstructure, nanostructure, superhydrophilic, superhydrophobic surface. What we are more interested in, what if we have the droplet in millimeter size and we have a structure with similar dimension? So we are using simulation. I'm using a scaled down model of Warwack et al. Ternary free energy ELBM, which itself is based on the ELBM done by Ilya Karlin. So it's a free energy base, and instead of using BGK, a single tau value for the collision operator, we are using alpha and beta. Alpha is the root of discrete entropy function. Beta controls the system viscosity, and this is the lattice Boltzmann equation. You have the distribution function after collision and streaming, the distribution function before collision, the collision operator alpha and beta, and at the right hand side we have the forcing term, which can either contain the chemical forces, the body force, or the solid liquid interaction. For the equation of state, we choose to use Carnot and Starling. We can obtain a density ratio to, I think, about almost 1,000. And for the solid fluid behavior, we introduced the forcing method. So we have this kappa W term, which will turn the surface to be either hydrophilic or hydrophobic. Positive kappa W means we have hydrophilic surface, like the left picture. And then for minus kappa W, which means we have hydrophobic surface, as can be shown on the right picture. We also have this rho rel or rho relative, which just scaled the local density value to make sure that this forcing method will just work on the liquid, not the gas. Therefore, it will be 1 when the local density is almost equal to the liquid density, and will be almost 0 when it's almost equal, when it's close to the gas density. On the right hand term is just a function which will check the direction of the solid. So if there are no solid everywhere, it will be 0. But if there is solid in one direction, it will be the value will be 1 times the weighting function. So from the experiment, we have a very, very wide parameter space. They have different mesh shapes in this picture, show as the phi tilt, the tilt of the structure relative to the z-axis, the phi rho relative to the xy plane. They have the pore angle, they have the pore size, the thickness of the surface, impact velocity, and etc. So we don't really want to simulate everything. There are just too many variables. We want to gain an insight on the structure behavior. Therefore, okay, let's just focus on these two-dimensionless numbers first. We play with the Weber number and the Bond number. For just a quick recap, Weber number compares inertial and capillary effects, and the Bond number compares the gravitational force to the surface tension force. So we obtain the experimental value of Weber number and Bond number, denoted by the asterisk, and then we use this value in our simulation, and then we vary the parameters. So we choose the Weber number, the 0.67, we call them WE, and 2.68 called 4WE. Why 4 instead of 2? Because we tune the impact velocity in our simulation. Therefore, doubling the impact velocity will quadruple the Weber number. For the Bond number, we choose from 0. We divide it from 0 to 1 into 0, quarter, half, 3/4, and 1. And we do it by tuning the gravity in our simulation. While in experiment, you can do it by changing the droplet size and by also scaling the structure size. We also vary the what we call the droplet impact position, because if we have a structure like that, the droplet can hit the structure in different position. Therefore, we also want to see how it will affect the collecting behavior. So in general, there are 6 outcomes depending on those factors. First, the one we really want to not see is the droplet penetration. So the droplet just hit the structure and then just penetrate, not capture at all. The best case scenario is when the droplet will just capture on the top of the structure, either just capture or rolling around, but never really penetrate the structure themselves. Or there could be a case where the droplet will penetrate. It seems to penetrate, but it still got captured by the inside of the pore. We also have another case where it penetrates, but it's not captured by the inside. It's actually captured on the bottom of the surface structure. There is also another case where the droplet will just bounce off the surface like this. Or if in some case, the droplet will be broken up by the structure themselves. So okay, let's focus on what we call this impact position. So the red area means we have solid. For the white area, we have pore or air, so there are no solids there. The gray circle is the droplet expected trajectory when it hits the structure. And we also have 2 arrows showing the droplet trajectory. So we have the diagonal one, which means the droplet will move from top right to bottom left, or we call them the 45-degree one. It will and 90-degree one when it moves from top to bottom. So we want to compare which one will control more between the Weber number and the Bond number at first. Okay, so we vary the Weber number, so we increase from WE to 4WE, and we don't see that much penetration. We just see that, okay, at lower WE, we found the droplet will capture on top. However, when we increase the WE, we see the droplet will bounce off the surface, but we don't see penetration, even though we increase the impact velocity. Next, let's see, what if we just fix the Weber number and let's vary the Bond number. At 90-degree, there is almost no change at lower Weber number. The droplet will just got captured, which is quite obvious because there are no pores. The droplet will just rolling on the top of the structure. While at higher Weber number, we don't see any bouncing behavior anymore. but now we see the droplet just got captured on the top. However, at different trajectory, now we can see penetration, which is caused by the droplet trajectory will make it move to the pore, or it will leave the solid structure. And even by a small amount of bond number, the quarter of the maximum value, we found that, okay, so the droplet can now penetrate the surface. So higher Weber number seems to determine at which bond number the droplet will start to penetrate, but still it's not really controlled by the Weber number themselves. So in this picture, we compare at half bond number and full bond number. At half, we see just penetration, but at very high bond number, we see the droplet to be broken up by the structure before rejoin again, and then just penetrate the structure later. So okay, what if we now move the impact position from this center, this junction, directly at the center between of those 4 pores, and now just move them halfway between these 2 pores. Okay, if we just vary the Weber number and then fix the bond number, we don't really see more penetration, because now the droplet, instead of bounce off the surface, it will be captured inside the structure, just like this illustration. So at higher Weber number, it seems to be able to get into the structure, but it can still be captured by the structure. But remember, this is at 0 bond number, so we can say, okay, we ignore gravity effect. However, when we put gravity, we see similar behavior with the previous impact position now. At certain bond number value, we see the droplet will always penetrate the surface, and the trend is the same. When at higher Weber number, it's easy to it will penetrate the surface more easily. So this is when, if we just see when it hits the center of the junction, it see penetration 45 degrees, because that's where the pore is located. While at this impact position, now it's happens at 90 degrees, because at 45 degrees now we see more solid, but at 90 degrees we just see all air on the droplet trajectory. So okay, so let's move the impact position again. Let's move them slightly downward, so slightly closer to the pore, but we change the droplet trajectory. Now, what if we move from bottom to top and bottom right to top left? So we see similar trend. We see that the Weber number doesn't really affect, but the bond number will cause more penetration, and trajectory also have a very high control, but whether the droplet will easily penetrate the structure or not. As you can see on the left figure, we see them at 27 degrees, while at the right figure, we see them at 90 degrees. So, however, when we see at this 15 degree or diagonal one, we see something a bit different. If we just focus on lower Weber number, we see similar trend. So it's captured, and at 3/4 bond number, the droplets start breaking up. However, we found re-entrance at higher Weber number, because at first it seems to just got captured. At 3/4, we now see droplet break up. However, when we increase the Weber number, now the droplet got captured again. So this is the illustration for 3/4 and full bond number. We have a couple of hypotheses. Our first hypothesis is, okay, maybe we need to run the simulation long enough, because usually we just, let's say, run it for a quite short time, and then let's see whether we can already see any of this behavior, whether it got captured or if just bounce off or it penetrate. However, what the simulation already done for 40,000 steps, and we see that at full bond number, it never really penetrated the surface, but at 3/4, we already see this behavior at well, just 25,000, 28,000, you already see the breakup. So discussing this with a member of our team, there's also a possibility that we are at this intermediate phase where the droplet is already moving. So we have this balance between the gravity and the droplet velocity themselves and the droplet trajectory. So it might be at 3/4 of bond number, we see the droplet is not really fast enough to just moving on the top of the surface, and it got pulled down and hence got broken up by the structure. Well, at higher bond number, which in our simulation means higher gravity, the droplet velocity, the droplet movement means it haven't really touched the inside of the structure and it will just rolling on the top of the structure. We also see this behavior not at different impact positions. So now we move them slightly. The droplet will hit at the corner of the pores at this different direction. And if we just focus on this region which I give this red rectangle, we see similar behavior. So at quarter bond number, it seems to penetrate, and then at higher bond number, it got captured. It just rolling around the top, and then if we increase the bond number again, it penetrates the structure, and it will do the same afterwards. So maybe it's the intermediate stage where we see this balance, and we are already in spatial or in the unique position. Hence why we see this weird behavior of this re-entrance. So in conclusion, we investigate a mesh-like macrostructure which have a water collecting ability, and we simulate at quite low Weber number. The droplet penetration is controlled not by the Weber number or the impact velocity, but more by the bond number and the droplet trajectory. So we already say that we want to explore more of the parameter space because it's very complex. It's not as simple as what we thought at first. But if we just run a simulation for all parameters, it will be very wasteful because it's very costly. Therefore, we choose this parameter, hoping we will gain some insight. But maybe we still need to do more, explore more of the parameter space. Maybe we play with different mesh structure because in the experiment they play with different pore angle. They play with 90 degree, 45 degree, and the angle between them. They also play with different ratio of the droplet size and the pore size. So it's also what we want to do. We also have another plan for maybe stacking the structure to see how that will behave. So thank you very much for listening. That's my presentation.
Okay, thank you, Raymond. Any questions from the audience? No, okay. Just a curiosity, how long does it take a simulation of penetration?
Sorry, can you repeat?
How long does it take one simulation? I mean, in your code, how many processors did you use? Some computational stuff?
Yeah, so I'm using, so the lattice size is 320 times 320 times 150.
Okay.
I usually run using 80 processor.
Okay.
It takes about 12 hours, I think, to do one simulation.
Okay.
Without processing any data, just running the simulation. Therefore,
sure.
Yeah, it's quite expensive too. Yeah.
Okay. I mean, I think you have already said, are you thinking to modify the shape of the mesh, of the solid mesh?
Oh, yeah. We also planning to, so currently the pore shape is just a square. Mm-hmm. So in the experiment, they also done a parallelogram one, and we also planning to do that. We already have the model, so we just need to pick our parameters carefully and then run the simulation to see. Mm-hmm. Maybe we'll see more insight of that.
I think that also the edge shape can influence. Now I think you are running with the sharp edges. If you introduce some curvature radius, improve or avoid the droplet penetration.
Yeah, that's also a possibility. Yeah. by playing with the roundness of the edges. Yeah, that makes sense. Yeah,
Exactly.
Thank you for your suggestion. It's really so. Thank you.
Perfect. Other questions? Okay, if not, let's thanks again Raymond and all the speakers of that technical sessions. We will close right now, and we'll meet in a while at 12 for the tutorial made by Bruce Bogossian. Thank you to all.